then we'll get going. So, okay, so welcome again to another SNAPP seminar. Today we have Henry Lam speaking. Henry's Associate Professor at the Department of Industrial Engineering and Operations Research at Columbia University. He got his Ph.D. from Harvard in 2011, has been in the faculty of Boston and Michigan universities before joining Columbia. He's interested in Monte Carlo methods, uncertainty quantification, data-driven optimization, and rare event analysis. He's been recognized with an NSF CAREER Award, JP Morgan Chase Faculty Research Award, and Adobe Faculty Research Award. He's also a long list of journals involved in areas to places like Operations Research, Journal of Computing, from Informs, Applied Probability Journals, Stochastic Models. So a good plethora there. He's also served on the Applied Probability Cluster organizing Informs. So, you know, a great contributor to the community. So it's my pleasure to introduce Henry, and he'll be talking today about cheap Bootstrap for fast uncertainty quantification. So great, thank you very much.
Thank you, Neil, for the very kind introduction, and also thank you, Neil, and the other organizers for the SNAPP seminar again for the very kind invitation. It's a great pleasure to be able to speak here. So today I'm going to talk about some recent work that I've been doing. And this work is about a general statistical methodology, but it has some particular implications in stochastic simulation and also in machine learning, where I hope you'll be interesting to all of you. And in the title here, there's a word called cheap, and there's another word called fast. So during the talk, I will, explain to you what I mean by all this. Okay, so let me just start with the problem that I want to sort of solve in this talk. I'm interested in a general inference problem, or some people would call it an uncertainty quantification problem, on some quantity that you need to estimate from data. So this quantity, it can be, just some elementary characteristic of a population, like the moment or the quantile, or it can be more complicated, like the regression coefficients or prediction from a machine learning model, or even the performance measure from a simulation model. And I believe for this audience, I don't need to stress that for general inference problem, resampling methods such as Bootstrap are very commonly used. And so the main goal of this talk is to introduce a method that I would call this a twist to the traditional Bootstrap methods to make it computationally cheap. So before I actually go into any details about this method, I will first spend perhaps a couple of minutes just introducing what is a Bootstrap. This is, hopefully this can refresh everyone's sort of memory and fix some notations. And also it will be a gateway to understand why Bootstrap is computationally expensive and hence motivate this work. Okay, so I'm just going to introduce a few notations. So throughout the talk, I'm going to use the notation psi to denote the quantity that I want to estimate. And in general, this quantity depends on the population or the data's distribution P. And in the data-driven setting, we don't really know what is P. But if we are given a data set of size n, then we know the empirical distribution P. So as I said before, this psi could be anything running from moment quantile all the way to the prediction of a machine learning model, etc. Okay, now when I say inference or uncertainty quantification, for the sake of this talk, I mean I'm going to construct a confidence interval for the true value of psi. And by this, I mean I want to find two numbers, L and U, such that the probability that the true value of psi lying between these two numbers, L and U, is approximately equals to some prescribed level, 1 minus alpha. So typically, we might choose alpha to be like 5%. So then we are talking about constructing a 95% confidence. Okay, so the main principle of Bootstrap is the following. Basically, Bootstrap approximate the distribution of a statistic by using the resample counter. Okay, so what I mean is the following. So let's say you have n data points and you construct an empirical distribution p hat. Okay. A very natural point estimate of the true value of psi is simply just to replace the unknown p by the empirical distribution p hat. Okay, so psi p hat is a natural point estimate for the true value of psi. Now, by resampling, I mean the following. So give me the data set x1 up to xn. I sample with replacement n times to obtain a new data set, x1 star up to xn star. So this x1 star up to xn star, each of them take value, one of the original data values. And so they can possibly overlap each other. And with this new resampled data set, I'm going to construct an empirical distribution P star, okay, and plug into the psi. Then I call this the resample estimate. So the Bootstrap principle basically says that the original point estimate and the resample estimate have a very similar distribution. So just to understand this a little more mathematically, typically when you have the original point estimate psi hat, you will satisfy a central limit theorem. Okay, so under some regularity conditions, we can show such a theorem that psi hat subtract psi true. Under the square root of n scaling, it would be approximately a normal distribution with some variance sigma squared. And so the Bootstrap principle says if I take the resample, which I call psi star, and subtract psi hat under the same scaling square root of n, it would be approximately a normal distribution as well, conditional on the data. And this normal distribution in the limit is the same normal as the limit theorem for the original point estimate. So intuitively, what it means is Bootstrap basically pretend that the data set is the population. Okay? And so you would replace P by P hat, and then P hat is going to be replaced by P star, which is sort of the empirical of the empirical distribution. And so because of this equivalence, now I can actually exploit sort of the same asymptotic limit between the resample and the point and the original estimate. And so one way to do it is the following. So because of this this equality in the asymptotic limit, I know that if I take the probability of psi hat minus psi true, it's roughly the same as the probability of psi star minus psi hat. But the nice thing about this is the right-hand side of this equation, you can actually run Monte Carlo to estimate the Qs, because everything on the right-hand side is actually known to you. You know psi hat and you know psi star, or at least you can compute all of them. So you can run a lot of simulation, estimate the Qs, and plug back these Qs onto the left-hand side. So that would give you a confidence interval for psi true. And in the literature, this is often called the basic bootstrap. Okay. Now, similarly, you can use the normal limit to construct a confidence interval. So that would be something like the normality confidence interval, where your goal would be try to estimate this sigma square. Okay. And so once again, you can exploit this same limit. And if you want to find the variance of psi hat, which is approximately sigma squared over n, then you can use the resample counterpart. You can take the variance of psi star, which you can compute by Monte Carlo again. And this is called a standard error bootstrap. Okay, so regardless of what you do using the bootstrap principle, I hope it's clear to you that you would require a sufficient amount of Monte Carlo replications, which I call B, in order to approximate either the quantile or the variance, okay, of the resample estimate. I would say, well, this is not an issue in classical problems. It could be a computational bottleneck in modern large-scale problems. So, for instance, imagine that the psi is actually the prediction output of a neural network, right? So if you want to run Bootstrap on a neural network, then it means that you need to retrain the neural network many, many times in order to construct some confidence interval. And beyond neural network, it could be the case that you are building other large-scale machine learning model where each run would require solving a large empirical risk minimization problem. So this makes Bootstrap computationally challenging to use. And on top of that, another sort of more subtle issue is it's actually not very clear what is enough Monte Carlo sample size be. Okay. So for this type of large-scale problems, even though there are some guidelines, in the traditional literature, perhaps like a large enough sample size B is more like a case-by-case basis. And this is actually something related to stochastic simulation. So on top of the computational challenges that I mentioned, there are actually some further additional challenges in using Bootstrap, especially in the simulation context. And I think by now it is quite well known in the stochastic simulation community, which is a problem known as input uncertainty problem. And what it means is the following. So in stochastic simulation, what we do is, we have a simulation model and we want to use it to estimate some performance measure by running a lot of Monte Carlo simulation. And typically, the simulation model contains some input parameter or some input distribution that needs to be calibrated. Okay? So for instance, if you run a queuing simulation, so take the notation that I used before, the psi here can represent the expected waiting time of some queuing network. And so this model, you can simulate it. And in order to do that, you need to specify to me what is the inter-arrival times or the service time distribution. And so psi is really a function of P. Now, as I said, this type of models, almost in all cases, these input parameters have to be calibrated from data. So for example, in this queuing system, perhaps the inter-arrival times and the service times distributions have to be calibrated from external data. Okay? And in this case, in fact, the performance measure that you try to estimate, your estimator would have two heads in your estimator. The first head is above the P, which is basically says that the input distribution itself contains some statistical noise from the external data. And the other head would be above the psi, which means given the input distribution or the input model, when you try to estimate the performance measure, you need to run Monte Carlo simulation. And so this Monte Carlo noise is going to be appearing as well, which corresponds to the second head above the psi. Okay. So there are two heads there, which means suppose you want to run a Bootstrap to construct a confidence interval for the performance measure, then you need 2 layers of sampling, where in the first layer, you have to resample the input distributions, let's say B times. Okay? And then for each resampled input distribution, you use it to drive many simulation runs, say R runs, and then you output the average. And at the end, you collect all these averages, okay? And you can use it to compute the quantile or the variance, just like the usual Bootstrap. But the challenge about this is now the total computational effort is going to be multiplicatively large. It's going to be a product of B and R, where both B and R has to be big. And in fact, just a little bit of more details. The problem itself is actually more complicated than I described. It turns out that because the overall variance in this problem is sort of has this entanglement between the noise coming from the external data and the noise coming from the Monte Carlo simulation, it turns out that in order to achieve consistency of your estimator, you need the number of resamples to depend on the original, on the external data size. And so what I mean here is not only does B and R has to be big, but it also have to be chosen in such a way that it depends on N in a proper way to make things work. So this adds to the sophistication in using Bootstrap in this problem. And I would say, just generally, this problem arises whenever there's uncertainty in both coming from both data and computation. So I don't want to go too much into this, but I just want to briefly mention that there are at least a few examples in machine learning that sort of encounter the same issue. So for instance, in deep ensemble means that instead of running one neural network to do a prediction, you train several neural networks. Each neural network use a different randomization seed. And then at the end, you take the average of all these networks to do your prediction. So once again, if you want to run Bootstrap on this, then you would need to do this nested sampling, where you need to first run B resample of the data, and then for each one, you run R training of the neural network. And similar problems arise when you use bagging, which bagging means instead of using a different randomization seed in each neural network, you first resample the data and then train some base learner. And then at the end, you average all these resampled base learner together. So once again, it has a similar structure as the deep ensemble that requires nested sampling when you use Bootstrap. Okay, so I don't think I would go into more, but the same issues arise when you try to use Bootstrap to assess the error of a Bootstrap estimate itself, which is the nested problems again. And there are also some works on using bagging bounds for assessing the quality of solution for stochastic optimization, which again have a similar issue. Okay, so given all these computational challenges, the question I want to ask and answer in this talk is, can we actually run Bootstrap with very few resamples? So since I am speaking here with this talk title, the answer is a yes. And I would actually show you that under almost the same regularity conditions as standard Bootstrap, you can actually use very, very few resamples to get to get a confidence interval that has desirable statistical guarantees. And I would also show you the price. And I would say that the price is a fair price to pay. I will describe more. Okay, so let's focus on the basic problem where I want to do inference on psi of p, where psi is a known function. Okay, so there is no sophistication of having to run nested sampling or whatever. Just a simple problem where psi is known, but p has to be estimated from data. Now the method that I'm going to present to you next uses a number of resamples b that could be as low as 1. So in terms of computation, this is the minimum possible you can get. And the method is the following. So suppose I have a point estimate psi hat from the data, and I have b resample estimates psi star 1 up to psi star b. I'm going to construct an interval that looks somewhat similar to a T confidence interval we've seen in statistics textbook, but some differences. So I'm going to take this point estimate psi hat and then add or subtract a T quantile times an S quantity. So this S quantity is the following. S squared is basically the variance of the resample estimates. Okay. However, inside the square, the center is not the sample mean of the resample estimates, but the original point estimate psi hat. Okay. And in the denominator here, I don't put b minus 1, as in the sample variance in a statistics textbook, but instead just b. Okay. And in the T quantile, the degree of freedom of this T distribution is b, okay, which means the degree of freedom is exactly the computation effort in the Bootstrap. So this interval is well defined for any b. Okay? So in particular, when b is 1, which means I use only one resample, okay, then the S will become the absolute difference between the single resample estimate psi star and the original point estimate psi hat. Okay? And the degree of freedom in the T distribution is 1. Okay. So is this interval a familiar interval? Well, if B is large, okay, we know that the T distribution that has a degree of freedom B is very close to a normal distribution. And so in this case, you can actually quite easily see that the procedure basically reduced to the standard error bootstrap that I have described before. However, the point here is you don't need a large b. B can be as small as 1. And in fact, I have this basic result that says if b is any integer, okay, under the typical assumptions that you make for standard Bootstrap, these assumptions are basically the assumptions that make the Bootstrap principle I described in the beginning of this talk work. It's the same type of assumptions. So under these typical assumptions, the interval that I just showed you in the previous slide is asymptotically exact as the data size grows to infinity. So that means that the probability that the true value of psi lying inside that interval is going to converge to 1 minus alpha. So I'm going to call, for convenience, that interval that I propose cheap bootstrap confidence interval. And cheap here means it's computationally cheap. You can use as small b as possible. And the proof of this is actually different from the Bootstrap principle I described earlier. Okay, so before I explain in more detail why this works and the theory behind, I'm going to show you some numerics which highlight what's the strength of this method. Okay, so this is the task here is to construct a 95% confidence interval for some the 60 percentile of let's say an exponential distribution, and suppose I have a data set of size 100. And this is a toy problem, but it would illustrate what's the difference between these methods and other methods. So I'm going to run my cheap bootstrap for different number of resamples, b, starting from b equals to 1 up to 50. And I also run the basic bootstrap, the standard error bootstrap that I described earlier. Here, I also run it on something called the percentile bootstrap, which is a variation of the basic bootstrap that exploits the symmetry of the limit distribution. And you can see that when b is 1, the cheap bootstrap already gives you a close to 95% coverage. Whereas all the other methods do not give you anything, because with just one resample, any quantile-based procedures cannot output you 2 quantiles that are finite. And the standard error bootstrap, you would put b minus 1 in the denominator for the standard error, and so you would output you something not making sense. Now, when b is 2, once again, cheap bootstrap will give you close to 95% coverage, whereas all the other methods will still give you something very far away from 95%, which is understandable because these methods are not invented to use a small b. Now, of course, when b gets larger and larger, then the other bootstrap methods would gradually catch up with the coverage level. So, for example, when b is 50, you can see that some of these methods are doing pretty well. Now, in addition to the coverage, another important criterion for a good confidence interval is the width. So here in the last column, I also show you these numbers, and you can see that when b is small, the cheap bootstrap has a long confidence interval, and when b increases, this confidence interval with actually decrease pretty sharply when b starts from 1, and then gradually it sort of still increases, but gradually levels off. So I've told you that there is a price to pay for this study, and the width is the price. Okay. With a small b, you would get a long interval. Now, I also want to say that, depends on how you think about it. This may not be the price for the cheap bootstrap. This is more like the price for using a very small b, because with a very small b, you don't expect to be able to construct an interval that is both short and also accurate. Okay? So in some sense, this is about the sample size itself. Okay, so I don't want to bore you with more numerics, but I can actually change the problem to, let's say, estimating confidence interval for variance And I try it for different grand truth distribution, and the same sort of observations would hold that cheap bootstrap consistently give close to 95% coverage. And in terms of the width, it's going to be long at the very beginning when B is small, but it would drop sharply pretty quickly. And the same goes for regression problem. And here what I do is I try to construct confidence interval for a regression coefficient with the feature dimension 100. And I try to visualize the result instead of putting them on a table. On the left-hand side, the graph shows you the coverage probability when the number of resamples increase. And you can see that cheap bootstrap, is pretty consistent, even starting from B equals to 1. It always gives close to 95% coverage, whereas standard bootstrap, it would be pretty bad when B is small, but gradually it would catch up. In terms of the confidence interval width, the middle graph and the right-hand side graph shows the mean and the standard deviation of the interval width. And you can see that cheap bootstrap initially has a long interval, but it would drop pretty quickly. Actually, even when B is like 5, it's already dropping to a pretty low level. Okay, so why does this work? So here's the Bootstrap principle that I showed you earlier, which says that if I take a resample psi star, I subtract psi hat, it would be asymptotically a normal distribution conditional on the data. Okay? And this normal distribution is the same normal that is the limit of the original CLT, okay, for the original point estimate psi hat. So the cheap bootstrap relies on one further steps coming out from this principle, that in fact, just by this equality in the limit between the resample estimate and the original point estimate, we can easily, readily derive that, in fact, psi star minus psi hat and psi hat minus psi true, they are asymptotically IID. So intuitively, this asymptotic IID is because of the fact that the resample estimates follow a conditional limit theorem, where the conditioning is regardless of the realization of the data. Okay? So regardless of what the data is, okay, the resample estimates satisfy the same CLT. And by this intuition, you can actually prove that these two quantities, psi star and psi hat, under the same scaling, actually are independent asymptotically. Okay? Now, because of this, this asymptotic IID actually allows us to extract information about the original estimate psi hat using very few resamples. And one way to extract information is to set up a t statistic. Okay? So in the numerator, you put psi hat minus psi true, and in the denominator, you put the variance of the resamples. And the numerator, if you multiply by square root of n, it will converge to a normal. And the variance at the bottom, when n goes to infinity, you can pull out some, the elementary properties of normal and chi-square, and you can see that it actually converges to the square root of a chi-square distribution divided by b. And more importantly, the normal and the chi-square in the numerator and the denominator, they are independent of each other. So they actually becomes a T distribution. And from there, you can extract the trip bootstrap confidence interval. So just in summary, basically, instead of using the resample distribution to approximate the original distribution for the statistic, the trip bootstrap exploits the asymptotic independence and normality between the resample and the original estimate. So that's the main idea. And just one remark about, I have been talking about the typical or the standard condition. Basically, if the functional psi is Hadamard differentiable with a non-degenerate derivative, everything will work. So this is the assumption that is required. Okay, I don't know if I should maybe have a pause here to see if there's any question.
So Henry, maybe a quick question on this last condition you mentioned. So like in a queuing simulation, I can assume that things are sort of not differentiable because busy periods can change if you change a few things locally. Is it sort of true for queuing simulations? Yep.
Yeah, that's a good question. So I think if it's a transient problem, then typically this would hold. Basically, this condition means, when you run the queuing simulation, when you predict the inter-arrival time or the service time distribution a little bit, the performance measure wouldn't change that much. It would be, there's a derivative there. But if you talk about steady state, then things might be a little more blurred. It might be harder to prove the differentiability.
Thanks.
Yeah, so in the remaining of this talk, maybe first I would make some remark about the half-width behavior. And then I will move on to talk about some other aspects of the trip bootstrap and also some generalizations of this method. First of all, regarding the half-width, so now that I told you, this actually is constructed from a T statistic. The half-width basically will follow the behavior of a T confidence interval. And here there are many numbers on this table, but maybe I will point you to the third column, the mean inflation relative to b equals to infinity. So what this means is if I compare the half-width mean of a trip bootstrap confidence interval versus the standard error bootstrap, where I assume I have full information about the variance of the resample estimates, which is computed from a normality confidence interval. What is the inflation of the half-width I would get? So for instance, if I look at b equals to 5, I have 24.8%. That means comparing the trip bootstrap confidence interval versus the idealized confidence interval using normal limit, I would get about 25% inflation in terms of so I mean, depends on what goal you have. It may or may not hurt you, but I would say it's pretty reasonable to get something as low as just if you have just 5 resamples, you get only a 25% inflation. It actually does not look too bad. Okay, so yeah, so I'm going to talk about maybe just a little more theory about the trip bootstrap, and then some generalization. So first of all, in fact, we could derive high order coverage errors for trip bootstrap. And in the bootstrap literature, the way to do it is use address expansion. And here, you could play the same game, but the issue is the trip bootstrap actually has an asymptotic that relies on a t statistic, not a normal statistic. So at least to my best knowledge, address expansions on t distribution is not available in the literature. And so we have to derive our own address expansions. Basically the result says that you know, the higher order error in the coverage is going to be of order 1 over n for a two-sided interval. And the coefficient in the 1 over n term, it doesn't have a closed form, but it is something that is computable by using Monte Carlo simulation. So this coefficient is b times the expectation of a Gaussian vector, okay? You know, and plus, you know, another expectation of another Gaussian vector. So it looks sort of ugly, but in fact, this is just the expectation of some function of a normal vector, and so it can be just easily, you know, computed by using Monte Carlo. But so the point here is, you know, actually this result match sort of the conventional standard error bootstrap and the basic bootstrap that I described earlier. They would have the same higher order term 1 over n. It's just the coefficient is different. And in terms of the generalizations of the cheap bootstrap method, in fact, I could apply the same idea to subsampling. Okay? So subsampling here means when you run the bootstrap, you don't, when you try to generate a resample data set, you don't generate a full data size. You generate a data size that is smaller than the original data size. And there are some reasons to do that. One of them is it avoids some, sometimes when the functional is not smooth, turns out that doing that could actually make the central limit theorem still work. Okay? And secondly, if you have a smaller data size than the original size, computationally, there will be an advantage as well. So here, in fact, the trip bootstrap idea can apply to different types of subsampling. So there's something called MO of n, back of little bootstrap, and subsample double bootstrap, and they all have a trip version. Basically, the trip version would be in the following form. You can actually use any b again, and when you output the confidence interval, you would have an s that sort of correspond to the different subsampling methods you use. And also, in addition, you have a scaling factor rho here that captures the ratio between the subsample size and the full data size. So, you know, the way to derive and prove this these intervals work would be very similar to what I have shown you before, except that you have to adapt the argument to these different subsampling methods. Okay, so one thing that I also have mentioned earlier is there's some, you know, a whole range of problems that require nested sampling when you run the bootstrap. Okay? And one of them is, you know, just like Varun's question earlier, regards, you know, simulation on queuing or other stochastic systems. Right? And in these problems, if your input distributions have to be calibrated from external data, and you also have to run Monte Carlo in your computation, then you will have two heads, right? And as we have seen before, you will need to run 2 layers of sampling in order to do the bootstrap. Now, the advantage of using a cheap methodology here is, in fact, here, when you run these 2 layers of sampling, the first layer, you can use b as low as 1. So in some sense, it avoids the multiplicatively large amount of simulation. Now, the only thing is actually, when you run the cheap Bootstrap for a nested sampling problem, the interval is less clean. Okay? So there has to be some modifications. Basically, the interval will still take a similar form. So your point estimate, psi hat, p hat, add or subtract some quantile times s. Here, s again is some variance estimate, calculated from the resamples. But q is the quantile of some distribution, which is different from a t distribution. So it's a bit more complicated, but it is still computable. Yeah, actually, the q, I don't think you have to pay too much attention to all the details here, but the point here is this quantile q is in some sense the quantile of some distribution that is a combination of normal and chi-square putting together. So once again, it can be simulated pretty easily. And I just want to say a few words about why this happens. It happens because in this kind of nested sampling problems, we have multiple sources of noises from both the data that is used to calibrate the input model and also the simulation error itself. And so if you want to play the same game of deriving a confidence interval by exploiting the asymptotic independence, it's a little more challenging, but not too much. Basically, this is the asymptotic independence I have shown you before. Okay? The asymptotic independence between psi hat and psi star. Now, suppose you have two hats in your estimates, then there are basically more randomness that need to appear in the asymptotic limits. And so it's not asymptotic independent anymore, but still it has a form that can be exploited. So that explains why why it is a little harder to construct that interval. And you can try this out, and you can see, again, compare this with basic Bootstrap and percentile Bootstrap. Yeah, so I'm not going to spend too much time on this table, but roughly speaking, I just want to say there are actually multiple ways you can construct cheap Bootstrap in the nested sampling situation. The previous slides, I provide you one way. In fact, that would be the first way, where I call this the center at original estimate approach. And you can have another approach using cheap Bootstrap as well. And you can see that the coverage is pretty good starting from b equals 1. Whereas if you use basic Bootstrap or percentile Bootstrap, it's going to be very far away from 95% again. And yeah, just for those of you who might have seen or read papers in the input uncertainty problem in stochastic simulation, there were actually a whole list of approaches that has been suggested before. And roughly speaking, almost all of them requires a large B and a large R. Except maybe the last one, which is batching and sessioning, which is not a Bootstrap approach, but you can also have computationally cheap performance. So I'm going to actually talk a little more about this maybe in the remaining few minutes. But yeah, but the message I want to say is cheap Bootstrap does have computational savings significantly compared to all these previous methods. And I think I will skip this, but you can try this on the deep ensemble problems that I mentioned earlier. So in summary, what I have talked about is what I call the cheap bootstrap methodology that can use a number of resample as low as 1. In terms of the theoretical underpinning, it uses the asymptotic independence between resample and original estimate instead of using the resample distribution to approximate the original statistics distribution directly. And it can work for basically, generic statistical estimation problems. And, it can be generalized to subsampling and nested sampling problems. Now, just maybe a final remark about the cheap bootstrap. So throughout the talk, I have been talking about comparison with other bootstrap methodology, but there are actually other methods for doing inference or uncertainty quantification using, for example, something called infinitesimal jackknife. So the infinitesimal jackknife means essentially delta method, which means you have to calculate the gradient. And in the literature, this is known as the influence function in non-parametric case. And depends on how complex is your model, the influence function may or may not be computed. Okay? But Bootstrap, you don't have to compute this influence function. Another approach is batching. So batching means you divide the data into different blocks. And then for each block, it satisfies a central limit theorem. And so you can actually pull together again using a t-statistic. Now, in some sense, the cheap bootstrap is similar to this approach, except that I would say when you use batching, there is a constraint about how many batch you can use. When you have a small data size, you cannot afford to divide. In fact, you might not even be able to divide into even 3 blocks, for instance. For example, if you have 30 data points and you use 3 blocks, then that means each data size in each block would be just 10. So in this case, the asymptotic limit induced by each block may not be accurate. Okay? So what I'm saying is there is a trade-off between the number of blocks and the sample size each block in batching. Whereas the cheap bootstrap basically is free of this constraint. Okay? So there's some advantage there. And then there are some in-between methods, such as batched jackknife and overlapping batching. So these are sort of methods that, it's not as rigid as batching, but in terms of flexibility, it also may not be as flexible as the cheap bootstrap, okay? Because basically these methods, you have to sort of configure, have a rigid configuration of how do you divide into blocks, etc. Yeah, I don't think I would have more time to go into more details, but something that is in current work about this cheap bootstrap methodology is try to understand it, how it works for high dimensional problems. Because in some sense, the reason why I want to have computational savings is because the problem is large scale. Okay? So it makes sense to look at what happens when there's a high dimensional setting. There are also more extensions on how to refine the high order accuracy of the cheap bootstrap. Application in online learning, where you can use Bootstrap to estimate the uncertainty for doing exploration. And finally, also looking at what happens if the data is serially dependent. So I'm going to end this talk. The main reference is the first one, but there are also some other related works that I also list here. Yeah, thank you for your attention.
Super, and I'd give a quick round of applause. Great. Okay, does anyone have any questions for Henry?
Hi, Henry, this is Venkat Anantram from UC Berkeley.
Yep. Hi.
Hi, I'm not sure I completely understood your notation, but your capital B, as I understood it, is the number of resampling. So each resampling itself requires you to take n samples from the original data sample of n points. Yeah. So then if that's the correct understanding, then one can even imagine studying a situation where capital B is somehow less than 1, because you might want to just sample fewer than n points from the original data samples, and there might still be some benefits. You could probably choose your confidence intervals according to some formula. So does that make sense, or is that so? When you think about capital B being less than 1?
Yeah, it makes sense. But perhaps I should explain more clearly. I think what you are pointing to is the subsampling. So just to clarify, there are when you construct a resample estimate, there are actually 2 steps. First, you need to sample with replacement from the data set to generate another data set.
That's right. Yeah.
So that data set has a size. That size is n in a typical Bootstrap, but in subsampling, it can be a smaller number.
Yeah, that's the idea. Yeah.
Now, I think it should be clear that this is not the computational bottleneck. The computational bottleneck is when you insert this data into the psi function. So that would correspond to evaluating, for example, use the data to run a regression or use the data to feed into some optimization. So that is the bottleneck.
Okay, understand. Okay.
Yeah. So that evaluation, B is the number of counts that you have to evaluate this bottleneck.
Okay, so my comment is more would involve somehow dealing with some kind of less refined version of psi to be able to figure out something that works, which is addressing a different direction from what you're looking at. I think. Yeah, okay.
Yeah, exactly. I think the subsampling where you use less than n in the data set, that would be the way you are thinking.
Yeah. Also, I mean, a related comment is also in the high dimensional case, the individual samples might themselves be high dimensional. And you could imagine savings by looking at some low dimensional projection of each individual sample somehow, right? So,
yeah,
I mean, that's also orthogonal to your ideas, but it seems like an interesting direction. Yeah.
Yeah, definitely. I was going to say that. Yeah. Thank you.
Thank you.
Great, thanks. Any further questions?
Yeah, I had like one question on, again, this Hadamard differentiability versus the infinitesimal jackknife that you mentioned. So is it fair to say that Hadamard differentiability is harder to satisfy than the influence function being smooth, because there you're just perturbing one sample, whereas here you're sort of replacing a sample with a different sample?
It's actually more general. I think there are some situations where you cannot have, well, depends on how you define the influence function. But Hadamard is supposed to be more general.
I see. Okay.
Any other questions? I had one quick, yeah.
I have a question about, so when you're thinking about implementing this in practice, so how should I, if I have some fixed budget of doing that, then how should I think about allocating it between B and R?
Yeah, that's a good question. So I'm thinking if there's a theoretical way to suggest. One way perhaps is to look at the coefficient in the address expansion. That might shed some light on what is a good allocation scheme. So for now, what I'm just thinking is just looking at the numbers that I generated. If B is like 3 to 5, for instance, so it's a pretty low number, but not too low, not like 1 or 2, then the performance is pretty good. So my current recommendation would be just pick B to be somewhere between 3 and 5, and then just do the allocation that way.
I see. Thank you.
Any other questions? I had one quick question. So in your numerics, it looked like the kind of coverage probability was kind of like spot on from like a really low value. And then you had some sort of higher order asymptotics, which seem to sort of say that goes down like sort of 1 over n, where n's the sample size and things like this. I wondered if you, but the thing that seemed to matter in the plots in the numerics was like the mean interval length started kind of quite high, but then went down quite rapidly. Did you look at the asymptotics of that at all? So looking at, say, what's happened to the mean interval length in terms of how quickly that might converge, because that seemed to be the thing that was sort of, that's where the trade-off is, isn't it? Obviously, there's an inevitable trade-off here, but I wondered if you looked at how that behaves. You might have put it on a slide and I missed it.
Right, yeah, that's a good question. So indeed, this table, I was trying to show that, but maybe I was wasn't too careful in explaining this. So in fact, about the mean interval length, because this is so first of all, there are actually 2 parameters here, n and b. N is the data size, and b is your resample number of resamples. So this table is showing the case where n is pretty big. So the data size is big, but b could be small, starting from 1 to 20. And then the graph that I show you is also a similar case where n is sufficiently large, but b can be very small. So here in this table, basically the second column, the mean, is indeed the mean of the confidence interval that I could sort of analytically approximate, because I know it is asymptotically a t distribution, so I could actually calculate everything by hand, which is the case where n is pretty big, but b is different numbers here. Yeah, so you could see that it's when b is 1 is a very big number, but then it drops very quickly, which is consistent.
Okay, so you could even numerically just calculate every single value essentially. So you don't need an asymptotic even for b, how it's going. If it ends infinity, how does it go down with b if it's here to mean? Okay, fine.
Yeah. So this is just like what you said. When asymptotically as n goes infinity, how does the width look?
Yeah. Okay. Great. That's good. Perfect. Great. Okay. Any other questions? Okay, and if not, I'll give one more round of applause for Henry. Thanks again.
Yeah, thank you very much, everyone.
And I'll stop the screaming now. If people did have another question, they can maybe quickly grab Henry.